Unmute.
So what are active galactic nuclei? So how would you differentiate between normal galaxies and active galaxies? So normal galaxy shines with the light of all the stars within it. So basically a galaxy spectrum is very similar to that of starlight. But in 1943, Carl Sagan noticed that there are some galactic spectra which are showing broad emission lines, and that is how this classification of active galactic current compact region around the center of a galaxy that emits a significant amount of energy across the electromagnetic spectrum. And this non-stellar radiation from an AGN is believed to be due to the accretion of matter around a supermassive black hole. So this is a schematic of what our current understanding is, that there is a supermassive black hole and you see an accretion disk. You can have features like an obscuring torus, relativistic jets, and regions such as the broadline region and the narrow line region. So now a little bit about the unified model. So this is an orientation based model. So in order to explain the different observational classes of AGNs, this was proposed. And this basically says that the way you look at the AGN is what you observe about the AGN. So you can see that if you're looking straight down the relativistic jet, then you characterize those sources as blazars, FSRQs, and BL-like objects. You have things like Seyfert galaxies in which are looking through the torus. That's why your view is obscured. And this is a brief introduction about that. So now we come to the crux of the matter. What is the motivation behind our work? So the low luminosity AGN population remains largely unexplored compared to the high luminosity ones. So in 2023, LHAASO came out with their first catalog of gamma ray sources. And LHAASO is the Large High Altitude Airshower Observatory in Tibet. And in this new catalog, they have basically talked about discovering many new pavotron sources as well as new sources of gamma rays. And one of the sources which interested us was this source, 1 LHAASO J 1219 plus 2915, which they have associated with a low luminosity AGN. And before the detection by LHAASO, all known very high energy emission AGNs were either blazars or FR1 radio galaxies with very large scale powerful jets. So since that publication of the LHAASO catalog, we have seen a lot of work done on this source itself, where you can see this group led by Wang, who have done a study of 5 such sources detected by LHAASO. And then you have a more deep dive by the LHAASO team themselves. This was published in August of last year, where they have done a separate work only on NGC 4278. And what basically this discovery shows us is that our understanding previously was that you need very large scale radio jets, sources like Cygnus A, which have hundreds of parsecs of radio scale jets. But now we are seeing that for NGC 4278, we have only parsec scale radio jets, but even those can efficiently emit TeV photons. So this is where our work comes in. So our work is basically I'm trying to model this source in order to understand and identify a possible emission region which can be responsible for this high energy emission. And simultaneously along with us, there was a group from China which was doing another work on this source itself. And later on, there have been 2 more papers published on this source in the last year. So a little bit about NGC 4278. It is an elliptical galaxy. It is located at a redshift of 0.02 with a luminosity distance of 16.4 megaparsecs. It is classified as a typical LLAGN due to the presence of its weak H alpha line. It has a central black hole mass of 10 to the power 8 solar masses and an Eddington ratio of order of 10 to the power minus 6, which indicates a radiatively inefficient accretion flow. Now, the previous paper by Lian et al., they have basically shown that NGC 4278 sometimes appears as a liner and sometimes appears as a Seyfert galaxy, depending on the X-ray emission. And because it is a low luminosity AGN, over the IR to UV wavelengths, it is dominated by the host galaxy and the dust emission. So now the VLB observation. So NGC 4278 was observed with an 11 element VLBI array on August 27, 2000. And this is the paper, Girolati et al. So what that has revealed to us is that it has a two-sided structure with S-shaped jets. And here you can see these jets, where you have a northern jet and you have a southern jet. And this entire structure extends over 45 milliards seconds, which corresponds to about 3 parsecs. So you can see that the scales are much smaller here. And it is classified as a compact symmetric object. So these are VLBA observations of this source at 5 gigahertz and at 8.4 gigahertz. So now what data from 95 as well and in the year 2000. So they have been able to overlay the two contours and they can see how the source structure has changed. So with that, what they have discovered is that the NGC 4278 has mildly relativistic jet, so beta of around 0.75, and the northern jet is aligned closely to our line of sight. So basically the northern jet is aligned to us and the southern jet is moving away from us. And they have derived the ages of each of these components. So they have also been able to identify radio-emitting components in the jets, which are S1, S2, N2, and N3, with S1 being the oldest component, around 66 years old, S2 and N2 around the similar age of around 30 years, and N3 component around 80 years old. So now we come to the LHAASO and the SWIFT observations. So LHAASO had been observing this source in their first observation run in January 2020 to September 2022. And their subsequent, later on the paper which I showed you, in that they extended this work till October of 2023. So LHAASO detected this source with their WCDA component, which is the water Cherenkov detector array, and not through their kilometer square array, which is the other component they have. And they have found that the best position fit of this source is within 0.03 degrees of NGC 4278, and it has been detected at a significance level of 8.8 sigma. And it has a variability timescale of months at the TeV gamma ray energies. So this is a picture of the LHAASO detector array in Tibet. And among the X-ray telescopes, it has been detected recently by the SWIFT XRT telescope on November 28, 2021. So this is during the LHAASO campaign itself. And what was found was that the nucleus of this source is at a high flux state in 2021 compared to the older Chandra observations in 2010. So what I have not mentioned in this slide is also that after the publication of our paper, in October of this year, the Fermilab collaboration has also shown that they have detected GV gamma rays also from this source. So now how do we model the radio components? So previously when you saw the VLBA observations, we saw that there were 4 radio emitting regions in the jets. So what we did is that we modeled these radio emitting components with synchrotron and SSC emission. So we have used the Gamera code to solve the transport equation as shown here, in which basically you can see that N stands for the number of electrons at a particular energy and time. Q is our injection spectrum, which is, we have assumed a power loss spectrum, since it is accelerated by a first order Fermi mechanism. B is our energy loss terms, and the escape time scale is the amount of time it takes to escape from this region, the accelerating region. And our injection spectrum is a typical power loss spectrum. So with this, with the plot on the left, you can see that we have been able to fit the flux from all these 4 emission regions. And this constraints our magnetic field within these regions. And then we can extend that that SED with SSC to try to fit the SWIFT XRT and gamma ray observations from LHAASO and the upper limits by Fermi. So we have used a time-dependent model to fit this SED because we say that it is a very young source, so it has not reached a steady state yet. And this plot shows the time evolution, how it affects the SED of a source. So what we can finally see that when you add up all these 4 radio-emitting components, you are unable to explain the SWIFT XRT observations and the LHAASO observations of this source. So that brings us, these are the parameters of all the radio-emitting components. So now the X-ray and the gamma ray modeling is basically what we say is there is an additional component in the jet which is responsible for such a high energy emission. And this is basically, this component is around the age of 30 years, which is comparable to our youngest radio emitting component. And we have basically used the same model for the radio components as well as for this. And these are our parameters for such a component within the jet. And now when we add up all these 5 components, we can finally explain the observational data across the electromagnetic spectrum. And what we can see is that the size of this emission region, this new emission region, is around 10 to the power 16 centimeters. This is the radius. And the magnetic field in this component is around 8 milliamps. And what we also found was that our parameters are constant, fit the constraints provided by LHAASO through their variability studies. And finally, what we learn about the source is that normally our understanding is that you have very high luminosity AGNs, which have also been explained by one zone as well as multiple 2-zone emission models. What we find is another entity they share is that the sizes of the radio emitting regions are much larger than the high energy component. And also what we have shown through our work is that the population of electrons responsible for the high energy emission is different from that responsible for the radio emission. And what this indicates is that even compact, less powerful radio jets can efficiently accelerate particles to emit TeV4. Thank you.
Thank you, Samik. Questions from the audience? Okay, so Samik, are you a master's student or?
Yeah, I'm currently a JRF at Bitsville.
You are a JRF at Bitsville. Okay. So I heard you talk before. A quick question. So you said that the mass of the black hole was what, 3 times 10
to the power 8?
solar?
Yes.
Yeah, 10 to the 8. So can you tell me how the mass of the black hole was measured?
I think that we have just seen from literature. I don't have an idea.
I know, but you cited some citations.
Yes.
Right? So I was curious if you know how the mass was measured, or generally how masses of black holes are measured. If you can just tell us, like maybe not this particular source, but any method with which you measure the mass of the black hole.
Sometimes I think you look at the luminosity and then you calculate through the Eddington luminosity case also.
Yeah, but it's not guaranteed that always black holes will be being Eddington.
Yes, so.
Okay. Thank you. Any more questions?
Okay, why you are interested to measure the gamma ray, not X-rays or something?
No, so basically what you see is that low luminosity agents have never been seen at TeV states. So this is the first ever discovery of a source like this, which is very low luminous in the radio wavelengths, to be present at such TeV gamma rays. Because I think previously there have only been like 5 sources, LLAGNs, which have been already seen by Fermi at GeV state. And this is the first ever to be seen at a TeV gamma ray state. So that way you have to think about. So basically you can. So the processes which are important for this LLAGN is the synchrotron and the synchrotron self-Compton.
Nuclei or electrons?
Electron population. These are leptonic motors, not hadron.
Any more questions?
I think it's out. So, so what is you said that you ended up concluding that there are different components emitting different dominating.
Yes, so basically the population of electrons responsible for the high energy emission is different from that.
Emission is being emitted. What is the Lorentz factor of that those electron distribution?
So the Lorentz factor of the jet is 2. The delta is 2.7. So these are the reference energies for our high energy compound, which we have injected around 10 to the power 5 GeV for is the minimum energy for our. So this is the maximum energy for our electrons, like the power law that we have injected in.
Okay, so when you are combining both populations of electrons, so the high energy part that is explaining the QV, gamma ray, and so on, they are also contributing to the radio, right?
No. So you can see that this is when it's crossing the radio, it's much lower. So the radio data is actually that. So this is not responsible for the radio emission. The radio emission has its own populations and the high energy emission.
All electrons are with some energy, they will emit.
Yes, but it's not a very high contribution.
Thank you, Shomita. That was a very nice talk.